That's it. Now, as you will see when we go over the spinal cord, next lecture or two, whatever, the spinal cord has spinal nerves that come out of it and go all over the body. Those spinal nerves are not part of the central nervous system, even though they're coming off of the spinal cord. They're considered peripheral. The brain has 12 pair of cranial nerves. Roman numerals 1 through 12. They have names, which we'll go over when we do it. And even though they come directly off the brain, they're not considered part of the central nervous system. They're peripheral. So just the brain tissue itself and the spinal cord tissue itself. That's it. Those are members of the central nervous system. And then as it says, peripheral is everything else. And it is. So all the nerves throughout your body, and the ganglia throughout your body, and the spinal nerves, and the cranial nerves, and everything there is that isn't the brain and spinal cord is peripheral. All right? Now, when we talk about the nervous system, we talk about incoming and outgoing signals. All right? So if a signal emanates from or originates in, if you will, the brain, move your left arm. Okay? That was a motor signal from the brain saying, I want those muscles to move and show the class how to move an arm. All right? That would be an efferent or motor signal. It's leaving the central nervous system and ending up in an effector. Okay? An effector, and in this case, the effector is muscles in the arm. Okay? And it ends up there. Those are efferent signals. Afferent signals are signals that are sensory, and they're coming back from the peripheral nervous system to the central nervous system. Now, clearly, if you think of that, say, well, okay, in my hands, I feel that this table is warm. I feel that this table is smooth. It has something of a grain to it, and all that's, go way back to the beginning of the semester when we did the skin, and you know those Meissner's corpuscles in the skin are telling me all that information about this tabletop. Right? That's an afferent signal going from receptors in the peripheral nervous system up afferent nerves back into through spinal nerves, which we'll discuss when we do the spinal cord, into the spinal cord, and now it's in the central nervous system, and with ascending tracts that we'll discuss something about when we get to the cord, ascending tracts going up to the brain to bring information saying that tabletop is smooth and has grain and it is warm and okay, so all that. And your brain interprets it. Right? So those are afferent or sensory signals. They start outside in the PNS and come back into the CNS. Now, when we talk about the peripheral nervous system specifically, because the central is really just anatomical, it's just brain and spinal cord. When we talk about the peripheral nervous system, we talk about two subdivisions, the autonomic nervous system, and that really means the automatic nervous system. Right? These are things that are going to take place in your body thanks to your nervous system that you have absolutely no control over. You don't even have to initiate them. They're going to happen on their own. Okay? And as I said, you won't have any control either, although it's been said that some people who really are deep into meditation can affect these. I've heard stories, heard stories that yoga masters, these guys who do really deep meditation, can actually slow their hearts down to the point where it almost looks like they're dead. But meanwhile, they're just in a really great state of meditation and the hearts are really going slowly. I mean, that's okay, it's possible. I don't know. I'm not going to deny it because I've never seen it one way or the other. But that would be your conscious control over an autonomic function. Your heartbeat is autonomic. The medulla oblongata, as you'll learn next semester, the medulla oblongata has the control for the heartbeat. You've got a pacemaker in there and an atrioventricular node, a whole bunch of stuff, which you don't even think about. Your heart is self-excitatory tissue. So if it's self-excitatory, I don't have to think about it. Anybody here thinking about their heart beating right now? Making it happen? No, it's doing it on its own. So you really say you don't have much control over it. Yes, things can happen where you can control it. You sit there and worry about the next exam, and all of a sudden you find your heartbeat goes up 15 beats a minute. Okay, well, sure, but you're not really consciously making your heart do it. You're worried about something, you're secreting more epinephrine, and your heart speeds up as a response to your worrying about the next exam. All right, so that doesn't really count as controlling the autonomic nervous system. But as I said, these guys can supposedly meditate to a point where they can actually slow their hearts down to from what I've heard, that some people can almost not detect the fact that they have a heartbeat. They think they're dead, but they're not. Obviously, you can't slow it down that much. You have to be able to find it. But at any rate, supposedly these autonomic functions in some people can be controlled. Okay. But generally, no. Excuse me. Anyway, the other branch, with the two branches of the other branches is well, okay, let's try that again. The somatic nervous system is the other one, other than the autonomic. That's all part of the peripheral nervous system. Somatic means the body, and the somatic nervous system strictly goes for the muscles, because that's the soma, the body that we're talking about. Okay, now, looking at the autonomic nervous system itself, forgetting the somatic, because that's pretty simple. We're going to talk more about that directly when we talk about nerves and synapses and stimulation. We already talked about with muscles. The other part, the autonomic part, is divided into the sympathetic and parasympathetic nervous system. All right? Now, as it says, sympathetic, and I use the word generally. Sympathetic is generally stimulatory. Okay? So that means that stimulation of the sympathetic nervous system is going to excite. Stimulatory, excitatory is a good word. It's going to excite something, whatever it is that the system is dealing with, whatever structure, whatever organ, whatever function, it's going to be excitatory. It's going to speed things up. So, as you can see, it's listed there, increased heart rate, okay? So, if we secrete more epinephrine as part of this autonomic nervous system, as part of the sympathetic, which you will, you'll speed up your heart. And you get vasoconstriction, which means narrowing of the blood vessels in the system. Systemically, we have vasoconstriction. That's going to raise your blood pressure. Well, why do you want to do that? Because something excitatory has to happen. And an increased blood pressure is good for the excitatory response. So you get more blood to those areas because you're raising the pressure. Okay? You can get vasodilation from this in certain areas, like the skeletal muscle in the heart. Because if you were going to exercise, you need to make your heart beat faster, so we're going to dilate those blood vessels and bring more blood to the heart muscle, and dilate the blood vessels to the muscles to bring more blood to the muscles, more oxygen, more food. All right, so that you're having both vasoconstriction and vasodilation depending on where you are. The vasoconstriction of the system raises the pressure so that when you dilate to the muscles in the heart, it gets a bigger flow of blood because the system is pushing more, thanks to the elevated pressure, all because of the sympathetic response. Your respiratory rate increases. Well, of course, you're exercising. You certainly need more blood, and you need more oxygen in the blood, so you can breathe faster. And of course, wherever glucose is floating around, you're bringing more glucose into the organs that need it. Now, when I said generally stimulatory or excitatory, the other thing on there is this, though. Slows down digestive system. Now that is not excitatory. That is inhibitory. So why is that? Well, it makes sense. When you're exercising or when you're doing a fight or flight response, which I put down right there, fight or flight response, that's going to stimulate the sympathetic nervous system. And it's protective. Because all these things happen, and basically you're trying to run away from, you're standing in a big open field, and along comes this bear, it's running towards you, it wants to have you for lunch. And you don't have a gun. It's just you and your fists. So you can either fight or flee. All right? Obviously the smart, intelligent thing would be to get the hell out of there if you can, and get away from the bear. I don't think it's too smart to say, oh, I can keep that bear up, he's not so tough. Okay, he might end up as his lunch. But nevertheless, either way, you've got to be able to move fast, get more blood to your muscles, get more blood to your heart, increase your respiratory rate so you bring in more oxygen. So you can do these things, either run away or just stay. And that's why we rely on this system to do that. Okay? And of course, epinephrine and norepinephrine, or adrenaline and noradrenaline. You didn't hear about noradrenaline, but you hear about adrenaline because that was the brand name that Park Davis put on it. It comes from the adrenal glands. When they figured out how to synthesize it in the laboratory somewhere in the 1950s, I think, or the late 40s. So they said, well, since it's a synthetic version of what comes from the adrenal glands, let's call it adrenaline. And to this day, people are still calling it adrenaline. However, the patent ran out, so there are about 150,000 generic drug companies that are producing adrenaline under the name epinephrine, which is its generic name, its actual name, hormone. So if you're ever working in the hospital, you're not going to see a little ampule of adrenaline. You're going to see one that says epinephrine. Okay? If you're working in a pharmacy, you're going to see epinephrine. All these generic companies are making. In fact, I'm not even sure Park Davis still makes adrenaline anymore. The patent ran out, so why should they harm it? But at any rate, this hormone and noradrenaline, or norepinephrine, mediate this whole response. So your adrenal glands get stimulated by the nervous system. As you will learn next semester, the adrenal gland has two parts, a cortex on the outside and a medulla on the inside. The cortex on the outside is under the control of a hormone called adrenocorticotropic hormone. So that can be secreted in certain times, but not for stress like this. The center, the medulla of the gland, produces the epi and the norepi, and that's completely innervated not by hormones, but by nerves that go in there. So it's the nervous system that's actually stimulating these secretions, and that's why you get a nervous response, a neurological response, to secrete epi and norepi, and to mediate this fight or flight response. So that's all the mostly excitatory. Why is the digestive system inhibited? Because if you're trying to run away from the bear, it really doesn't pay to try to digest food at that point. And your body's going to say, look, I'm putting a good amount of blood into this digestive system to keep it functioning so it's digesting food. If you die, the food's going to die with you in your gut. So let's shunt some of that blood away, vasoconstriction there, and because you only have 5-6 liters of blood, that's it, and you got to move it around. You know, it's sort of like money. If the government decides there's a deficit, it would not behoove them to say, let's just print up a whole lot more money and cover the deficit. We need $1 trillion, print $1 trillion. You can't do that. Then your money becomes useless. That happened in Germany in the 1930s. I don't know. Anybody ever learned about that? They were walking around with wheelbarrows full of money. You know, a loaf of bread was like $150, but $150 didn't really count like $150 does today. So, point is, you don't want to do that. So we can't come up with more blood. We got 5 to 6 liters. That's all you got. You got to move it around the body where it has to go. So the sympathetic nervous system stimulation will move the blood away from the digestive tract by constricting it, slowing it down, and move it into the areas you need it in, like your heart and your muscles. Okay. The parasympathetic, which is the other half of the autonomic nervous system, is again generally inhibitory, not excitatory. And what is that? Well, your system is going to vasodilate, unlike the other way, which we had vasoconstriction. So we're going to lower your blood pressure. Certain blood pressure medications are classified as parasympathomimetic, meaning it mimics the parasympathetic nervous system. You take this medicine and what does it do? It dilates your blood vessels in the system to lower your blood pressure for people with high blood pressure. In fact, if you ever watch some of these commercials, I haven't seen as many as in the past, but Cialis or Viagra commercials on TV, you know, for erectile dysfunction. If you look at those commercials, they always say somewhere in there, if you're taking blood pressure medication, or they may mention a few specific ones, check with your doctor first to see if you can take this. Well, here's the reason. Blood pressure medications, parasympathomimetics, will generally dilate your blood vessels. There are others that work that in different ways, but they'll dilate the blood vessels to lower the pressure because you have high blood pressure. Viagra and Cialis work by dilating blood vessels, particularly the penile arteries, to bring more blood flow to the penis so you can get a better erection. That's the whole way it works. So if you're already dilating your systemic blood vessels because you have a high blood pressure situation, and you take an additional drug to do some more dilating, you can get seriously low blood pressure. So that's why they say in these commercials, you know, talk to your doctor if you're taking these blood pressure medications, because you don't want to overdo it and really dilate like the parasympathetic system does. So many blood vessels that you end up collapsing because your blood pressure's in the toilet. You don't want that. So that's why you hear that on those commercials. So the parasympathetic will dilate the systemic circulation. The blood vessels will lower the blood pressure. It will vasoconstrict to the muscles and to the heart somewhat, because the idea here is you're going to relax. You're going to eat your dinner. Here's the stimulatory one. It will stimulate, will increase the blood flow to the digestive system, and also stimulate the secretion of gastric juices, gastric enzymes, and digestive enzymes, because you're supposed to be digesting. So the trick is, when you finish eating your dinner, you're not supposed to be running outside and exercising. I'm sure you all know that. Okay? And you're supposed to just sit back and relax, have an after-dinner drink, smoke a cigar. Okay, you don't have to. It sounds like something relaxing, right? If you like cigar. Just take it easy and let your body digest the food. So we're getting excitatory activities of the digestive tract and inhibitory everywhere else. So that's what the parasympathetic does. So that's why we say generally, because that digestive tract works opposite. Okay? So when you're stimulating, the digestive tract gets relaxed, and when you're relaxing, the digestive tract gets stimulated. But otherwise, everything else follows suit, with the sympathetic being excitatory and the parasympathetic being inhibitory. Okay. This is a good chart that comparing the two in several different areas. Okay. First off, the sensory input of the somatic nervous system versus the autonomic. All right. Again, as I said, somatic really refers to the muscles, mainly. That's it. And autonomic is all that other stuff that you have no control over. So, as you can see, sensory input from the somatic is going to be senses and special senses. Somatic senses and special senses. So, pressure, temperature, touch, okay, and special senses. Input, smell, taste, hearing. All of the five senses, basically, is what you're going to get there. The autonomic nervous system, as it says, interoceptors. Okay, an interoceptor is a receptor inside your body. How do you know you're not hungry anymore? All right, your hypothalamus, as you'll learn when we do the brain, and again next semester when we do the endocrine system, the hypothalamus has in, among many other functions, the appetite control center, and also the thirst control center. So when it reads the bloodstream and sees your sugar levels are low, it turns on the appetite center and says, you should be eating, your sugar's going down. If it sees your water levels are low, it says, you're getting dehydrated, you should be thirsty, go take a drink. All right, but there are other interoceptors that, see, this isn't really like an interoceptor, but there are stretch receptors in your stomach. And when food gets in there and it stretches out, it sends a signal back to the hypothalamus and says, just want to let you know, we just ate a 7-course meal. So the hypothalamus says, well, based on what I'm getting from the stretch receptors, interoceptors in the stomach, you're not hungry anymore. Look at all the food you ate. All right, so, that's one example. Anybody here just before class stop in the bathroom and pee? Okay, you don't have to really raise your hand. But point is, why did that happen? Interoceptors, stretch receptors in your urinary bladder said to your brain, hey, go to the bathroom, I got a lot of pee in here that's got to come out. Okay, and you went, now you feel better, because the bladder shrunk back down, and the stretch receptors go, oh, nothing happened in here. And that's it, so you don't go to the bathroom. So that kind of stuff is interoceptors. Within the organs and other parts of the body that are telling your brain something's going on within the system, not that this is cool or smooth or, no, that's your somatic nervous system. All right, what about control of motor output? Okay, well, somatic is voluntary. As it says, cerebral cortex. Cerebral cortex, the outer part of the brain, says, oh, I'm thinking. Hey, raise that left hand. Boom, okay, that was somatic. It worked those muscles. All right? Contributions from basal ganglia, which is in your brain. We'll talk more about that later on. The cerebellum, which means little cerebrum. It's the back portion of the brain, a separate structure from the brain itself, which regulates balance and motor coordination. So input from the cerebellum tells your brain a lot. All right? It gives it information that it's picking up from receptors in parts of the body. Right? At the end of the nervous system lecture, we get to the eye and the ear. And the ear is very much responsible for your balance. Okay? And very briefly, and we'll get into more detail, the structures inside the inner ear that regulate balance have fluid in them, and it moves in relation to gravity. So if I tilt my head back, I'm not fooling my cerebellum thinking I'm walking uphill, because there are receptors, interoceptors, throughout my body telling it, hey, but you're standing up straight. I'm not going to modify your posture just because you're tilting your head. You're not going to fall over. However, if I was going uphill on an inclined plane and my whole body was tilting, and my head too, it would say, gee, I'm getting from the fluid in there that you're going uphill, but I'm also getting from the interoceptors throughout your body that you're going uphill. So I'm going to modify your posture so that you don't fall backwards. Now, obviously there's a limit. If the thing was like this, I'd fall backwards. But if it's just a decent incline that you might fall if you didn't lean forward a little bit, you don't even think about it. You just lean forward automatically because of interoceptors between the ear and the body telling the cerebellum that you're going uphill. And you know, if it's steep enough. If it's not very steep, it's not going to matter. But if it's a steep incline, we use those interoceptors. Okay? Brainstem, spinal cord, we have all kinds of motor output from there. You know, to control various things, which we'll discuss when we get into those segments. As far as the autonomic nervous system motor output, well, this is, again, it's automatic. So, as it says, involuntary control from the hypothalamus. And that's going to be things like I said, like, okay, you're hungry, eat. You're thirsty, drink. All right? It also controls your temperature in there. And that's completely out of your control. You don't have to do anything. It just takes care of it automatically based on all kinds of information that the body's giving it. We'll talk much more about the hypothalamus. It does a whole host of things, which I'm not going to get into now. The limbic system. Okay, this is also part of your autonomic nervous system. The limbic system is known as the seat of emotion. And when we do the brain, we're going to talk more about that. How many people took psychology here? Oh, most of you. So it's not going to be anything new for most of you when we talk about Phineas Gage. Yes, of course. No good psychology teacher worth their salt doesn't talk about Phineas Gage. And in fact, pretty much every class when I ask that question, we do teach about Phineas and what went on and why it went on. Every student says, oh yeah, we did that in psych. But yeah, we'll do it again, so at least it'll be familiar. You might learn a few things that they may not have told you. Like, his skull is on display, did you know that? And the tamping rod that went through his skull is on display next to his skull. I won't tell you where. I'll tell you, you have to come back to that one. It's in a place when I tell you, you say, oh, makes sense. Anyway, the brainstem is the midbrain and the pons and the medulla, which we'll discuss when we do the brain. That's got a lot of input, you know, as far as motor output. It controls things, and we'll get to that. And it says limited control from the cerebral cortex. That's because that's the thinking part. And this is autonomic, and your thinking isn't really doing much. Like I said, you can speed up your heart by getting nervous, thinking. Your brain is thinking, oh my God, I got this test, and I haven't studied enough, I'm going to fail, oh my God, I need to get into that program, oh my God. Yeah, well, you're going to get your adrenal glands working and pumping out that epinephrine, and that's going to affect your heart rate, and your sweating, and your blood pressure. Okay, so yeah, you know, I mean, there's your limited control, but generally it's not like, you know, I think I'd like to lower my blood pressure now. Now maybe, of course, you can by meditating is going to do it just because you slow the body down altogether. That'll help, but generally no, you're not. It's very limited from there. The motor neuron pathways. Okay, I'm going to talk about a motor neuron in a minute. One neuron pathway in the somatic nervous system, that's going to the muscles. Somatic motor neurons from the CNS synapse directly with the effector, and as I said, in the case of the somatic, the effector is the muscles. So nerves coming out of the central nervous system through those spinal nerves are going to travel down and innervate the muscles that are doing these things. Okay, we talked somewhat about that when we talked about muscles. So we'll get into it in a little more detail. As far as the autonomic motor neuron pathway, it's usually two, not one. Okay? Ganglion is a cluster of nerve cell bodies. Right? So the preganglionic neurons, those before we get into this ganglion, this cluster of nerve cell bodies, from the CNS, synapsing with the postganglionic, those after this control area, all right, in the autonomic ganglion. Basically, these are going, as you see, it says, to a visceral effector. Viscera are organs. We're not going to muscles, as we said. That's strictly somatic. And the muscles don't overlap. They don't get into the autonomic at all. They're somatic. So the viscera are going to react, stimulating your intestinal tract. All right, that's autonomic. Just to speed up. Okay, it's time. We have to digest the food. Or speeding up your heart, or slowing down your heart, or slowing down your gut. Okay? okay, or causing other organs in the body to do something in response to neurological stimulation. We're not talking about hormonal stimulation. Next semester, when you get to the digestive system, you'll learn about the gallbladder. Gallbladder responds to a hormone called cholecystokinin. It's a hormone. The hormone gets the gallbladder to squeeze and release its bile that it's storing. You know, this is not really an autonomic nervous system. This is a response. Labor is not through the nervous system. Oxytocin, we talked about that at the beginning of the semester when we talked about homeostasis. Oxytocin comes down and says to the muscles in the uterus, 85% smooth muscle, contract, we got to get rid of this kid. So that's not, you know, that's hormonal. That's not really the nervous system involved in that. So you got to separate the two. But that's what you see there. Neurotransmitters and hormones, well, strictly, that's it. All somatic motor neurons release only acetylcholine. That's it. Acetylcholine, as we talked about with the muscles, is the one and only neurotransmitter that makes this stuff happen. Okay, there are no other neurotransmitters for that. In the brain, yeah, because the brain's telling me to move my arm. So sure, in here there's various neurotransmitters causing communication between nerves in the brain. You have 100 billion. They're communicating and they're using different hormones, different neurotransmitters. All right, but here, that's it. Get those muscles moving, acetylcholine, period. All right, now, neurotransmitters and hormones, you notice there's a whole lot more written under the autonomic nervous system. So all the sympathetic, parasympathetic, preganglionic neurons, they do release acetylcholine. So we got that in the central nervous system as well. However, there are many others, norepinephrine, and what they're not listing here, there are also various hormones that are in the central nervous system, serotonin and dopamine and GABA and glycine and a whole host of, glycine is just an amino acid, it acts as a neurotransmitter. A whole host of different neurotransmitters, which we'll talk about more when we get to the central nervous system. But all you have in the somatic, acetylcholine, that's it. It's just move muscles, that's all. All right, the effectors, well, as you can see, muscles, that's it. That's all it is when we talk about somatic, the body. The other things that aren't in your control, smooth muscle, so dilate, constrict blood vessels. Move the food through your intestinal tract with peristaltic wave motion. The uterus going into contractions, semen being moved forward, and sperm coming out in an ejaculation. All this stuff is going through there. We're not talking about moving those muscles, we're talking about moving smooth muscles. And cardiac muscle, changing your heart rate up and down. And glandular secretions. Okay? All that stuff is operated by the autonomic nervous system through other various pathways, neurotransmitters, etc. And then what kind of responses? Well, in the somatic nervous system, when the muscle contracts, that's a response, period. Very simple. Somatic's easy. See, there's not much print there. Okay, that's it. With the autonomic nervous system, you got the smooth muscles contracting and relaxing in various areas. The heart beating stronger or weaker. And glands secreting or not, or cutting back on their secretions. All that out of the person's control. So this is a good way of comparing the two systems and seeing in each category how they're different, and they definitely are. The only overlap we have at all in this whole thing is that there's acetylcholine in both systems, but it does different things. In the somatic, it's just operating the muscle. In the autonomic, it's doing several things in the brain, to regulate various, and it's more excitatory neurotransmitter, but it's there. Now, when we talk about the nervous system, we talk about the neuron. The neuron. A neuron, now this is a multipolar neuron, or a motor neuron, or a motoneuron. Sometimes when they put it together, they take the R out, called a motoneuron. Same thing, and multipolar, okay, fine. This is in the peripheral nervous system only. What you see there is a peripheral nerve, okay? And it's not in the central nervous system because of its structure. So let me explain what I'm talking about. Remember that both of them, whether it's in the central nervous system or the peripherals, and there are neurons in the central nervous system as well. They don't undergo mitosis in either place, okay? And they are cells, even though they don't undergo mitosis, and they have a cell body, which this book calls the soma, cell body. Okay. Some books call it a soma, which means body, or a neurosoma, which means nerve cell body. But here it just says cell body. And of course it has a nucleus, okay, which is right there, and it has a nucleolus right there. It's just like a cell. It has organelles within the cytoplasm inside the nerve, but it has special structures on it. One special structure are the dendrites out here. These guys, these branches, dendrites, receivers. Okay, why are they receivers? Because they're going to receive, they have on them receptors for a particular neurotransmitter. In the case of the somatic nervous system, ACH. Alright? So acetylcholine is going to come down. We don't have a synapse on here. Okay. This would be a postsynaptic nerve. There would be a synapse, another nerve up here, let's say, that wants to communicate with this one. So it would send down its axon, which they have. The axon, in the case of the peripheral nervous system, is coded, now it's red here, actually it's white, because myelin is white, it's not red. But if the artist made that white, you wouldn't see it, it would blend in with the background. You know, so we're stuck with red just because it looks good. But it's really white. Myelin is a fatty substance and it's white. Okay? So, and when we talk about the brain, you're going to hear about the white matter and the gray matter, and why it's white and gray. Meanwhile, this is coated with this white fatty substance called myelin, insulating fatty layer that speeds transmission. And yes, it does. When it's functional like it's supposed to be, when it's in the proper amount on each of the axons, the wire, if you will, that leaves the cell body, comes down this way and conducts electricity. Electricity is conducted through a nerve cell in one direction only, unidirectional, under normal circumstances. If something else goes wrong, it's another story. But under normal circumstances, it'll come from these dendrites that are picking it up from a previous nerve, a presynaptic nerve, carry it through the body, carry it down the wire, the axon, which is coated by myelin. The myelin is produced by Schwann cells. This is, again, in the peripheral nervous system only. Schwann cells, which have another fancy name. When we get to the central nervous system, I'll mention the fancy name to compare it to the one in the central nervous system that does the same thing, produces myelin. Gets to the end, to the axon terminals, and you see it says transmitters. The axon terminals, just for a second here, there's the axon, here's the axon terminal, or the terminal end bulb, okay, or the terminal button, depends on the book, inside of which are little vesicles. The vesicles contain these red balls. The red balls represent neurotransmitter. Okay? Now this could be anywhere. This doesn't have to necessarily be central, peripheral nerves. This could be central too, because the process is the same. What happens is, as the axon receives that electrical impulse, that action potential, it hits here. The vesicles will move towards the cell membrane here on the axon terminal, merge with it, doesn't open up, can't open up because it has to merge so that the integrity of the axon terminal remains intact, it has to stay closed. But it will dump its contents into the synapse. So all these red balls representing a neurotransmitter. On the other side, the postsynaptic nerve, the dendrite there, so one of these, has receptors. There they are, those little things with the flat surface. The receptors are for that specific neurotransmitter. The neurotransmitter gets there, attaches to the receptors, and now the impulse that came down and caused these things to get released can jump across, pick up on the dendrites of the postsynaptic nerve, travel through the soma, travel down the axon, and go here and maybe communicate with another nerve. Or, as we discussed with muscles, communicate with the motor end plate on the muscle, which has receptors for acetylcholine, and being that this is in the peripheral nervous system, it's probably secreting acetylcholine. All right? So the acetylcholine comes out of there, the motor end plate picks it up, the impulse jumps across, the muscle contracts. All right? So we should know muscles at this point. All right, and that's, yeah.
So the one for this picture, the one with the axon, is that the presynaptic nerve that it's given? And that
Right.
dendrite is...
This here is releasing neurotransmitter. There's the synapse, the gap. This is before it because the flow is in this direction. So yes, that's a presynaptic nerve releasing neurotransmitter. That's a postsynaptic nerve receiving with those little receptor sites right there. They're proteins. And we talked about that. You remember when we did muscles, we talked about myasthenia gravis, where the body's immune system attacks its own receptors for the neurotransmitter? That's it. it'll be attacking these guys, so there's fewer of those. This would really represent a motor end plate in that case. But the same concept. They pick it up, and if you have fewer of them to pick it up, even though you have plenty of the red balls floating around inside the synapse, you don't have enough on the motor end plate to really stimulate the muscle properly. It'll stimulate, but it'll be a weak stimulation. So that's what the problem is with that disease. And somehow we have to treat it so that even though the body's immune system continues to knock out these receptors, you can still get impulse enough to get the muscles to move. And as I said, they have these treatments with interfere with acetylcholinesterase so that the acetylcholine stays around longer. Maybe get some higher production of acetylcholine to increase what's in the synapse. Do whatever you can to flood that motor end plate. All right? Well, in this case, it's just two nerves, presynaptic nerve and the dendrite of the postsynaptic nerve, picking it up so it can now travel on down the nerve and go where it has to go. All right? So that's a close-up of that. In between, and you're going to get this in lab. Well, I know I put this out in my lab. I can't speak for other teachers. A lot of them don't even know that there's a nerve model in the closet. I've been here long enough, so I know. But there is a nerve model, so if your teachers actually take it out, there's two models actually. One is more complete, except it doesn't have axon terminals on it. But it does, they're glued to the body. It's funny how they do it. The other one's in two pieces. They take the axon and put it separate on the board from the soma, from the body. It's still there, okay? Anyway, you look at that, and you'll see these things, and you'll get to see the dendrites, and attached, what they have attached to the dendrites are axon terminals that look like this. But where they are is here, instead of at the end of the nerve like that, because they're trying to show you the actual synapse. But of course you can't, because the synapse is a space. And you can't get these axon terminals to float above the dendrites. Oh look, there's a gap in there. No, you can't, so they're glued. You have to sort of imagine that there's a space there. But the little axon terminals about that big, sticking off of the dendrites on the model. Anyhow, in between each of the segments of myelin, individually secreted by an individual Schwann cell in each one. So this has 7 sausages. I would say it's like a link of sausages. 7 sausages of myelin here. That means there are 7 Schwann cells secreting each individual group. The myelin is from that one cell. That's how it works. All right. In the central nervous system, we got a whole different layout. It's still myelin, and it's still insulating the nerve, the axon, but it's laid out differently. We'll see that when we get to the central nervous system. Anyway, so that's basically your motor neuron. There it is there, and that's it. And space between each of these is called the node of Ranvier. Okay, so it's not. Here's a wire. This is insulation, the black stuff. Okay, basically it represents myelin, except it's continuous. We just don't have that. Even in the central nervous system, there's always a little gap between the sausages. You know where the sausages get tied together on the string? That's the node of Ranvier. Okay? Well, you see the sausage is here, the sausage is here. There's a little space in between. Obviously they're tied together, but this doesn't tie. This is an actual gap in the layout, in the deposition, if you will, of the myelin. Right? So that's a node of Ranvier. And this myelin sheath helps to speed up the transmission. Right? Nerve transmission in a standard myelinated nerve can be as fast as 300 meters per second. So are you aware of the fact that a meter is like a yard? It's bigger, 39.37 inches instead of 36. That's over 900 feet per second. That's how fast you transmit a nerve impulse on a myelinated nerve. Which is why, when I touch this, it's instantaneous. I feel it, but the split second that my finger touches it, there's no lag time. Why? Because it certainly isn't 900 feet from my finger to my brain. All right? I wear a 35-inch sleeve, and you got a little extra distance here, maybe, 8 inches. So that's 43, and then up to the brain is another 8. So it's about 51 inches from my fingertip into my brain. All right? Certainly at 900 feet per second, 51 inches is not a bad, it's like, forget it, it's a drop in the bucket. Sure, there's some sort of a lag time there. It's probably 1/10,000,000th millionth of a second or something. But nevertheless, okay. So without the myelin, though, now there are some nerves that aren't myelinated naturally in the body. Pain nerves are not myelinated. It's a little bit of a slower process. They still conduct, but they do it much more slowly. Myelinated nerves like this one, and this is in the peripheral nervous system, so you don't see this happen. But in the central nervous system, same myelin, same function, insulating the axon, speeding up the transmission up to 900 feet per second, over 900 feet per second. Sometimes there is one disease particularly that causes destruction of the body's myelin. Your own immune system attacks the myelin. Which one? MS, multiple sclerosis. And it's in the CNS. It's not, you don't have it like, oh, well, it's in my arm and, I can't feel things properly or my muscles don't work. No, it's in the central nervous system. It's always in the brain and spinal cord. You can see it on MRIs. They look for what they call MS plaques, P-L-A-Q-U-E. And when you see these white areas, you know that the myelin's been removed by the immune system for reasons we don't understand. Okay? So it slows down transmission, and it's progressive. And as such, people start losing function. They'll start having trouble with their muscles. They won't work as well. They won't respond as quickly. They finally get to a point where they really can't walk well. I talked with somebody who had this. It's the great crippler of young adults. 20s, 30s, 40s. You're not talking about old folks. Oh, I've been around 80 years. I found that it's very unlikely that an 80-year-old is going to get MS. And unfortunately, it's people your age. But it's there, unfortunately. I heard a story once when I was a kid, and it stuck with me. My mother worked with this woman in an office, and she came home and told me this story. I guess that's been about 11 or 12. And she knew I was interested in medicine, so. Girl, she had an 18-year-old daughter. And she filled the bathtub, and she reached in with her hand and said, okay, the water's a good temperature, I can take my bath. And then she put her foot in and burned her foot. Her hand told her the wrong information. So somewhere in there, and of course they didn't have MRIs back then, so they had to go by symptomatology to diagnose it. Now we can run an MRI in the central nervous system, look for these plaques, and see that the myelin's been stripped off the axon. But then they didn't, they had to go by symptoms. And they diagnosed her as having MS. So, I have no idea what happened to her. She was 18 back then. I don't suspect for a minute that she's still alive, because it is a progressive disease. You can't stop MS from progressing, but guys can't take advantage of this. Only women can. You get pregnant. Strange, but there's a reason. When you get pregnant, your immune system gets mildly suppressed so that you don't reject the baby. Okay? And therefore, suppressing the immune system helps it not attack the myelin. And it kind of doesn't make you better, and it all grows back, and oh boy, we can start from scratch again until we have another kid. No, but it stops the progress. And so people feel better because they're not progressively getting worse over the 9 months. Once the baby's born, the immune system comes back to normal, and it's like, oh, we'll keep attacking that myelin. Why, we don't know. Anyway, that's your peripheral nervous system, motor neuron, multipolar neuron. And here's a nice electron micrograph of axon terminals. You can see that little enlargement there, all those little bulbs there. And inside are vesicles with the neurotransmitter. And this is the cell body of a postsynaptic neuron. It's the cell body there. So they're communicating with that nerve. Different kinds of nerves. Different shapes, different styles, what they do, different functions. Okay, we've got the bipolar or interneuron. Now, when we do the spinal cord, we're going to see these interneurons. They communicate between incoming afferent signals and outgoing efferent signals in the spinal cord itself without any intervention or involvement of the brain. Eventually, the brain gets involved. But we'll save that. We'll talk about the simple reflex arc when we do the spinal cord. Okay? So these interneurons, these bipolar neurons, are in there communicating between afferent and efferent signals. Okay. The unipolar or sensory neuron, well, that's what sensory looks like. So there's your dendrite there, and there's a dendrite there, and these are the axons here. So the dendrite comes in, the cell body's off to the side, and then the axons down here. Sensory neurons. So these are the ones that are associated with your Meissner's corpuscles and your Pacinian corpuscles and your hair root nerve endings, the ones that tell you that your hairs are being moved. Okay, all those are feeding back through nerves like this. Okay, the third one, of course, is what we just looked at, the multipolar or motor neuron that we just looked at in the PNS. And lastly, in the brain, we have these pyramidal cells. So So the cell is a little tiny cell body right there. This is all dendrites here, and that's axons there. All right, we see those in the brain. Okay. Now, in the nervous system, we have, and again, none of these nerves, none of these neurons undergoes mitosis. That's the unfortunate part, because if we can get them to do that, we can certainly heal up and quickly regenerate nerves that were damaged in the spinal cord, for example. Spinal cord has a whole bunch of nerves going up and down, ascending tracts, descending tracts, we'll talk about it, okay? And if they were damaged, and we know if they're not able to repair themselves, you lose some function. However, we can get these things to undergo mitosis, that would be great, but they don't. We're working on that. They've been doing stem cell injections, trying to get them to get in there and differentiate into a nerve. Having some success, but.
How do they repair themselves with satellite cells and muscles or?
No. In other words, same with the muscle cell, you don't need a satellite cell. There are satellite cells in the nervous system, but they're nothing to do with that. You don't need a satellite cell to repair a muscle. If the cell is not damaged beyond repair, it's a cell. It'll undergo the normal healing process, generate what it needs, do what it has to do, change its metabolism to work towards healing. And then it heals. That's it, just like your skin. Or you burn your mouth on a hot coffee. And it lasts a couple of days, and all of a sudden, hey, it feels fine. It's gone. Your cheek cells regenerated. That's great. Okay? If they didn't regenerate necessarily, they might just repair themselves. Well, the nerves can repair themselves as long as they're not killed off or the damage is so severe that they can't repair. Okay? There is nothing like a satellite cell to replace a nerve like we did with muscles. Even that's limited, but at least we can do it sometimes. And if you don't have a repetitive stress injury with the muscles, then that repair should hold. But if you keep doing the same thing and you keep damaging the same area, eventually you run out of the satellite cells and then you end up with scar tissue on the muscle. But with the nerves, it doesn't work that way, unfortunately. Satellite cells have another function, which we'll get to. So these cells, these neuroglia, okay, or glial cells, these undergo mitosis. All right? And there are 6 different kinds, 4 in the central nervous system, 2 in the peripheral nervous system. Okay? So these have different functions. Obviously, that's why there's 6 of them. And as I said, they do undergo mitosis. So they have a whole different function. They're also much, much smaller than neurons. Here's a slide. Okay? And you can see, obviously, the neurons. These are all somas you're looking at. 1, 2, 3, 4, 6, 7. There's 8 neurons in this picture. Okay? And you can see coming off of the axons and the dendrites. There's an axon. The dendrites are here. The axon, I think, is going up. These are dendrites here. The axon's coming off this way. There's an axon there. So you can see that. All right. Now, in the picture, you also have what looks like dirt. All these little black dots. These are all different kinds of neuroglia. So you can see how much smaller they are than the neurons. Okay. In your brain, as we will mention again when we do the brain, mass-wise, you have 50% neurons and 50% glial cells in the brain, in the central nervous system. Okay, but numerically, look at if those little tiny guys are going to take up half the mass compared to the big cells there that take up half the mass, clearly they outnumber them 100 to 1. All right? I mean, well, figure out. I mean, you got 8 here. If you took the time to count all the little black dots, you see how many you have in one field compared to 8. I'm not about to take the time. You want to do it for fun. I bet if I offered extra credit, I said, you get 10 extra points on your, he's going to see I do something.
Got it.
No, I was just kidding, of course. But seriously, you can see they're far outnumbered. Glial cells far outnumber neurons in the central nervous system and the peripheral too. But this is a CNS slide. Anyhow, so these guys, there are these different kinds. There are 4 kinds in the CNS rather, and 2 kinds in the PNS. All right. So this is a nice drawing. An astrocyte. Well, somebody thought that the cell, which you can see right there, looked like a star. So they called it an astrocyte. And we'll get to what they do. This is an oligodendrocyte. This is the guy who's the counterpart to a Schwann cell. He's going to produce myelin. Okay, and then you can see the little bit instead of red, this one's blue. But okay, or purple. Anyway, there. So 1, 2, 3, 4, 5 different pieces of myelin laid out there. But there's something different about this is the way it's done compared to the be PNS. We'll get to that in a minute. Microglia. Micro means small. Oh, look at the little tiny cell body. There they are. These are phagocytic. We'll talk about that in a second. And then these guys here, the ependymal cells. You find these in the brain, and they're involved in the production of cerebrospinal fluid. We'll talk about that. All right, so let's talk about one, the microglia first. Phagocytic. What do? Because they're phagocytic, they're going to clean out dead tissue. Cells die for various reasons. Maybe they age out. Remember, because none of the neurons are going to undergo mitosis, but they age out. Maybe they're damaged by something. Okay, so these guys will clean that out. Also, if there are any invading viruses or bacteria, they will valiantly attempt to kill them off. Now, there are conditions that when we talk about neurological diseases, there's viral meningitis, there's bacterial meningitis. So they're going to go after the viruses and the bacteria. Not always effective. And the viruses, they work very nicely because it is a self-limiting condition. We'll talk about it. But for the bacterial, if you don't treat with antibiotics, you're dead. Plain and simple. But we'll get to that. So these guys are involved in that. Now, the oligodendrocytes, the most abundant of all these glial cells are the oligodendrocytes. These are the counterparts to the Schwann cells. These produce the myelin, but in a different way. It's the same substance. But the axon is myelinated somewhat differently. It's still going to be in segments. I'm changing battery. That. And it's still going to have a little node of Ron VA in between. But look at how it's laid out. On the peripheral, in the peripheral nervous system, on the axon, you had a Schwann cell, made its myelin. Another Schwann cell, made its myelin. Another Schwann cell. So in the picture, we had 7 different sausages of myelin, 7 different Schwann cells, period. Not here. Here, an oligodendrocyte can service several axons, and an axon will be serviced by several oligodendrocytes. So it's not isolated to the one nerve. So if you take a look, let's bring this up a bit. It's like an octopus. This octopus, this oligodendrocyte, is servicing this axon here from some nerve over there. He's servicing this guy in 4 places. He's servicing this axon up here in 2 places, and that guy's being serviced by somebody else here that's coming off from over there. So it's a lot of sharing with the oligodendrocytes and the axon placement on several different neurons, and each neuron receiving placement from several different oligodendrocytes. Now granted, the PNS, you're getting, in the picture we had 7, it was 7 different Schwann cells, but they were all isolated to the one axon. They weren't coming from other places. In this, there's sharing going on. Okay, that's the oligodendrocytes. The astrocytes, as I said, are star-shaped and involved in supporting neurons, transmitting impulses because they work with electrolyte balance, particularly potassium, and making up part of the blood-brain barrier. Now, what you're seeing, and we have like 1 minute, so I'll try to finish this. If not, we'll just pick it up. What you're seeing here, there's your astrocyte. This is a capillary. Now, the blood contains certain chemicals that are really not good for the brain. So, we don't want those chemicals oozing out. Remember, capillaries we've talked about. You'll learn more about them next semester. Capillaries are selectively permeable, and things pass through them. So your nutrients pass out of your bloodstream into the tissues. The waste products pass into the bloodstream to get processed. Oxygen goes into the tissues. Carbon dioxide comes out of the tissues. Electrolytes and hormones get delivered. So things pass through. Well, there are chemicals we don't want in the brain. Waste products that haven't been filtered out yet. These astrocytes put their little feet out there, podocytes there, put their feet out on the capillaries, and they stop stuff from getting through. That's the blood-brain barrier. Okay, so they're regulating electrolytes to help the brain work better, and they're also protecting the brain from certain chemicals in the bloodstream that we don't want getting into the brain. So that's the blood-brain barrier. Okay? Next, lastly here, in the CNS, the ependymal cells, these guys at the bottom, the pink ones. Okay? The ependymal cells are in the ventricles of the brain, and we'll talk more about that when we get to the brain, producing cerebrospinal fluid, and also forming the blood cerebrospinal fluid barrier. Once again, in the cerebrospinal fluid, we don't want a bunch of junk getting in. So these guys, instead of putting feet out, they're packed tightly together, and there's very little space between them. Only certain small molecules can get out of the bloodstream, like blood plasma, which is predominantly water, and glucose and very tiny proteins, and urea can get in there, and several other chemicals. When we get to the cerebrospinal fluid, we'll show you a breakdown. They can squeeze through between those tight junctions and get into the ventricles and become cerebrospinal fluid. Other chemicals are kept out by the tight junctions between these ependymal cells, and they line these ventricles in a structure called the choroid plexus. We'll get into that when we do the break. All right, we'll stop here. We'll pick up with the PNS on Thursday.